Okay, so now they want us to do some more interference, but they want us to use some speakers, which is a little different for us, but that's okay. It's still waves. We can handle it. No big deal. All right, so let's see where we are. All right, so it says two small speakers are positioned at a distance of 0.75 meters from each other, as shown in the diagram. The two speakers are emitting a frequency of 2500 hertz. So here's our D, here's our F, here's our L, and someone's standing right here. Here's a maximum as expected, okay, and then he's going to travel to point Q in a minute, but right now all they want us to do is find the wavelength of the sound. Well, the speed of sound is equal to frequency times wavelength. So if we want the wavelength, we're going to take the speed of sound, which is 343, and divide it by the frequency, which they told us was 2500 hertz, and get our wavelength. And when I did that, I got a wavelength of, if I can find it wherever I wrote it down, 0.1372 meters. 0.1372 meters. So there's our wavelength for our sound. All right. Now the student moves a distance d, a distance y, to point Q, and notice that the sound intensity is now at a minimum. Okay. Calculate the shortest distance that the student could have moved to hear this minimum. All right. So I said, well, I know that a minimum occurs when I'm out of phase. All right, so I need to look at that angle. And what did I find out? I found that angle was 5.25. So let's look at how I got that. So I had m lambda equals d sine theta. So m would be a half, because that's my first minimum. My wavelength is 0.1372. My D, 0.75, that's how far apart my speakers are, which we used right here. Okay, sine theta. So I found out that theta was 5.25 degrees, so that's small enough so that sine theta and tangent theta are about the same. So if I know that this is 5 meters, I'm looking for this distance from here to there. I'm going to call it y. And this is my theta. I can say that the tangent of theta is equal to y over 5 meters. So the tangent of 5.25 degrees times 5 meters should give me y. Well, when I did that, I got y to be equal to, let me see my work, 0.0459 meters, 0.459 meters. So we moved about 46 centimeters, basically, which is not very far at all. Okay? All right, so we did part B. Now, let me clean this off, and we'll scroll up and look at the next part, C and D. All right, so let's come on down here. Okay. All right, so we did that right there. We calculated the shortest distance. Now it says identify another location on the line that passes through P and Q where the student could stand in order to hear another minimum. So if P was here, this is my line, and that was point P, and he was over here for point Q. He could come over here the same distance, 0.459 meters, and hear another minimum. Now, I could have reworked it and said that I had m lambda is equal to d sine theta, and I could have substituted in 1.5 m and done the same work and found how much farther it would have been down there. But to me, it just makes more sense if I already know this, just move him above P instead of below P, and it'll work. All right. And then D says, how would your answer change to part B if the speakers were closer together. So we had M lambda equals D sine theta. So this is not going to change. That's going to stay constant. So if this gets smaller, this has to get larger. So the angle theta is going to get larger. Is everybody okay with that? And if the angle theta gets larger, then this, since I know that tangent of theta goes up as well, and that's equal to x over L. If this didn't change, but this went up, this has to go up. So the distance between maximums or minimums is going to change. It's going to increase, all right? And then 2 says, how would your answer to part B change if the frequency emitted by the two speakers was increased? All right, so what I said was, well, if frequency goes up, then the wavelength has to go down. And if the wavelength goes down, coming back right here, then if that goes down, this stays constant, that stays constant. If this goes down, sine theta has to go down. And if sine theta decreases, then the separation, the distance between maximum to maximum or minimum to minimum is also going to go down. All right. Okay, so I'm going to pause for a minute and go to the next. Okay. I'm not sure if I'm going to be able to write yet. Come on, board. Nope, that's what I was afraid of. All right. Okay, so now I should be able to. All right, it says 2005 B4 says your teacher gives you a slide with 2 closely spaced slits on it. She also gives you a laser with a wavelength of 632 nanometers. Laboratory task you are assigned asks you to determine the spacing between the slits. So I'm looking for D. All right. These slits are so close together that you cannot measure their spacing with a typical measuring device. Okay, so it says, from the list below, select the additional equipment you will need to do your experiment by checking the line next to them. So I would want a meter stick, so I can get the distance from the screen to this lovely little slide that I've been given. I would want a tape measure, I would think. I would want a screen to show my light on. And I think that's about it, okay? Draw a labeled diagram of the experimental setup that you would use. Okay, so I said, well, that's the line I'm interested in. Here's my slide over here. Here's my laser out here. And I can't draw a laser, so I'm going to pretend that's a laser. All right, I'm going to call this distance from here to here L. And then I'm going to say that there's maximum here, and I'm going to call that my Y value. And that's the distance from maximum to maximum. From maximum to maximum. All right. And this line right here is called my screen. Better label that. Okay, so that's all I have. All right, so we did part B. Part C says, on the axis below, sketch a graph of intensity versus position that would be produced by your setup, assuming that the slits are very narrow compared to their separation. All right, so it's going to look something like this. And I could do a lot better job if I would just make these all should be about the same size. Okay? All right, so there's that one. All right, D says, and now they want me to outline a procedure. So I'm going to get rid of this and scroll down. Okay. Okay. So outline the procedure that you would use to make the needed measurements, including how you would use each piece of additional equipment you checked in A. So I said I would shine a laser through the slide. All right, I would measure with meter stick the distance from the slide to the screen, which is L, what we're calling L. That's what we're calling L. And then I would use the ruler or the, I guess I said tape measure, use tape measure. To determine, D-E-T-E-R, sorry, I can spell, distance from max to max. And I think we call that Y. Alright, let me see if I said anything else. Nope, we're good there. Okay, the E said using equations show explicitly how you would use your measurements to calculate this slit spacing. So M lambda equals D Y over L. So if I wanted to find D, I would say M lambda L over Y should be equal to D. And I know that I would do 1 for the first central maximum. My lambda was 632. L, I don't know, I'd have to measure it, and Y I would have to measure, but that would give me my D. Alright, I'm going to stop this one and we'll get some more done.